Hey everybody, welcome to the module on the stability of the nucleus. The nucleus is a component of the atom. This is first proposed by Rutherford in his atomic model. As we now know, the nucleus has a positive charge because it contains positive charged particles called protons, as well as neutral particles called neutrons. These two particles are often referred to as nucleons because they are found in the nucleus. By applying our current knowledge of classical physics, there are two forces present between nucleons: gravitational force and electrostatic force. The gravitational force is attractive and exists because nucleons have mass, and the electrostatic force is repulsive and only exists between protons as neutrons are not charged. Since we know the masses of protons and neutrons, we can use Newton's gravitational force formula to calculate the magnitude of the attraction based on the average separation distance between them. This gives us this following magnitude. Likewise, since we also know the charge of a proton, we can calculate the magnitude of the electrostatic repulsion between them, and this gives us roughly 230 newtons. As you can see, the magnitude of the repulsion is many orders stronger than the attraction due to the gravitational force. This should raise the question: if the repulsion is much stronger than the attraction, what is keeping the nucleons together and preventing the components of the nucleus from disassembling? The answer to this question leads to the introduction of a new type of fundamental force, that is a strong force. This is sometimes also called the strong nuclear force because it is found between nucleons in the nucleus of the atom. The strong nuclear force exists between neutrons and protons and mediates the stability of the nucleus. What this means is that the relatively large magnitude of the electrostatic repulsion between the protons we calculated earlier is overcome by the presence of the strong nuclear force. Here's what you also need to know about the strong nuclear force. It only acts over a short distance, and when I say short, I am talking in terms of femtometers, and 1 femtometer is 10 to the power of minus 15 meters. When the distance between the nucleons becomes longer than 2.5 femtometers, the strong nuclear force diminishes to insignificant magnitudes. The strong nuclear force is also normally attractive, and the magnitude of this attraction is the greatest when the nucleons are about 1 to 1.5 femtometers apart. Another really interesting property of the strong nuclear force is that it becomes repulsive when the nucleons get too close, especially when the distance becomes shorter than 0.5 to 0.7 femtometers. This is illustrated by this diagram, which shows you the relative magnitudes of the electrostatic force, which is always repulsive, and the strong nuclear force, which is normally attractive, but suddenly becomes repulsive when the distance between the nucleons becomes too short. So returning to the Rutherford's atomic model, there are three forces present in the nucleus: the gravitational force, the electrostatic force, and the strong nuclear force. The magnitude of the gravitational force is insignificant compared to the other two, as the mass of protons and neutrons are extremely small. Now that we know the forces present in the nucleus, let's discuss what makes it unstable in more detail. The stability of the nucleus is governed by the balance between the strong nuclear force, which is normally attractive, and the electrostatic force, which is normally repulsive between the protons. A stable nucleus requires a specific ratio of neutrons to protons to achieve this balance. When there are too many protons, the electrostatic repulsion outweighs the attractive force. This is because the distance between protons inevitably increases with how many there are. When the distance between protons becomes greater than 2.5 femtometers, the attraction due to the strong force quickly diminishes, while the repulsion due to the electrostatic force remains present. So when there are too many protons, there will be too much electrostatic repulsion. While the number of neutrons does not change the magnitude of the electrostatic repulsion, it does affect the nature of the strong force. When there are too many nucleons in the nucleus, which includes both protons and neutrons, the much stronger attraction causes the average distance between the nucleons to become shorter. When the distance becomes less than 0.5 femtometers, the strong force suddenly becomes repulsive. Now, as you can imagine, having two repulsive forces in the nucleus is not good for maintaining its stability. And this is why a nucleus can also become unstable when there are too many neutrons present. I want to reiterate this concept I just discussed because it is very important in understanding nuclear stability. The stability of a nucleus is determined by its composition, that is, the number of neutrons and protons. Protons provide electrostatic repulsion and strong force, which is again normally attractive, while the neutrons can only provide the strong force as they are neutral and uncharged. When the number of protons increases, the magnitude of the electrostatic repulsion also increases, and this becomes greater than the attractive force due to the strong nuclear force. This is due to the increasing distance between the protons as the nucleus gets larger. This is why as the proton number increases, more neutrons also need to be added to the nucleus to stabilize it by providing additional strong nuclear force. However, when there are too many neutrons, this is also not good, as a strong nuclear force can become repulsive due to the decreasing separation distance between the nucleons. There are a couple of good rules of thumb to remember when it comes to nuclei that are unstable. Generally speaking, large nuclei, that is when the atomic number is greater than 83, in other words, when a nucleus has more than 83 protons, are unstable. A good example of this is uranium, which has 92 protons. The second rule to remember is the neutron to proton ratio of a nucleus. A stable neutron to proton ratio for small elements, generally this is regarded as the first 20 elements, is 1. That is, one neutron requires one proton, and if we have this 1-to-1 ratio, then the nucleus is considered stable. However, as the number of proton increases, so as the atomic number increases, more neutrons are required to stabilize the additional repulsion between the protons. This causes the neutron to proton ratio to increase with the atomic number. So as the atomic number increases, the neutron to proton ratio becomes greater than 1. If you plot all the stable isotopes of nuclei on a graph where the y-axis is the number of neutrons and the x-axis is the number of protons, this is what you can produce. The region in which all the stable nuclei or isotopes are found is known as the zone of stability. And any isotopes and nuclei outside this region are considered as unstable. It's important to realize that the zone of stability deviates from the straight line, which represents a neutron to proton ratio of 1. Previously, we said that for small elements, the neutron to proton ratio is 1. This is why at the bottom left of the graph, the zone of stability is on top and very close to this line. However, as the proton number increases to the right, the nucleus gets larger, and the required neutron to proton ratio to achieve a stable nucleus becomes greater than 1, resulting in the blue zone or region to deviate from the line. We'll discuss this graph of different unstable nuclides in more detail in the video on radioactive decay. This concludes the video on nuclear stability.